Test, test. People on Zoom hear me? Hello, can people on Zoom hear? All right. People in the back? All right. Good afternoon. How's everyone doing? Woo! All right. Let's finish off the RISC-V instruction formats from yesterday. So just as a reminder, last time we finished up 5 of the 6 formats that we'll be discussing in RISC-V. We had the R types, which are used for arithmetic operations, I types, which are used for anything with an immediate. We had the S type instructions, which are used specifically for store instructions, B type instructions, which are used for branch instructions, U types, which are used for those special LUI and AUIPC instructions. And there's one last instruction that we didn't cover. That's the JAL instruction. And that'll be our J type instruction format. So remember when branch equality had like this really weird pattern where you store bit 12, then you skip 11, you store 10 through 5, then you do 4 to 1, then 11? J-type's worse. Here's the instruction format. We store bit 20, then 10 to 1, then 11, then 19 to 12. It feels random, but there's a good reason behind this. So first off, we need to store one destination and an immediate. Same as with the branch type instructions, we don't store bit 0 because bit 0 is always going to be 0. But if you look through this, you can see kind of a pattern here. First off, the most significant bit, it's always the largest bit. Bit 31 is always going to be the sign extension bit. That's why I put bit 20 at the top. Bits 10 through 1, they're actually in the same place as bits 10 through 1 as the I-type instruction. So that simplifies the circuit overall. Bit 11 is kind of just placed randomly. And then bits 19 through 12 get placed in the same place as the U-type instructions bit 19 through 12. So there are these patterns here. You can kind of see the intent behind why they designed it this way. But you don't really need to know that. You just need to memorize this pattern. You don't even need to memorize the pattern because it's available for you on the reference card. So there, jumps have 21-bit immediates because we don't store that last bit. So we can go up to 2 to the 18 instructions up or down. So here's the JAL instruction, the one instruction that uses this. In effect, what it does is it sets the destination register to the PC plus 4, so the next line. And then it sets the program counter to the PC plus offset. So basically the difference from where you are currently to the location of the label. And the label must be within 2 to the 18 instructions. Otherwise, the JAL instruction just doesn't work. Any questions? Why is the pattern 1 indexed? Well, because we don't store bit 0. With the J-type instructions and the B-type instructions, we're dealing specifically with instructions, right? A jump of a certain number of instructions. And each instruction in RISC-V is 4 bytes long. So because of that, if we're just counting the number of bytes we need to jump, we'll never have an odd number of bytes. So bit 0 is always going to be a 0. Technically, bit 1 would always be 0 in RV32, but some extensions of RISC-V use 16-bit instructions, so that's not necessarily true for all versions of RISC-V. Yeah. Any other questions? All right. Want to do one last practice round? All right. One last practice. What instruction formats do you want to do? How many people want R-type? I, S, B, U, J? Yeah. All right. Seems like people want J. There were a few people who wanted B, so I'm just gonna 3/4 chance for a J. Let's run this. Which direction do you want to go? Binary or value? Or instruction first? How many people want binary first? Instructions? This is evenly distributed. I do have a quarter. All right. Heads for binary. It's binary. All right. So let's run this once. All right. Hello? Hello? Why is my keyboard not working? Okay. I'm gonna close this and just reopen another one. CS61C, summer 25. All right. Python-u random RISC-V.py. All right. Let's try evaluating this instruction. 0x FF9 FF66F. I'll give you. Let's do this until 220. How are people doing? How many people need another minute? All right, let's give another minute or so. All right. People doing all right?
Yeah.
How many people are done? How many people need another minute? All right. Still feels like there's some people who want to finish. I'm gonna give another 30 seconds or so, and then I do need to move on. All right. Let's bring everyone back. All right. What did people get? JAL A2, I hear JAL A2 minus 6, and I hear JAL A2 minus 4. Anyone get something else? You got minus 4?
Oh, it's minus 8.
It's minus. Yeah, there is an implicit 0 there. The answer I got was JAL A2 minus 8. But again, I might be wrong. I'm a bit rusty with my translations. Let's see what the answer is. Drum roll, please. JAL A2 minus 8. All right. So yeah. Keep in mind you have the implicit 0 there, so you do need to double the value of the immediate if you're just writing it out and not writing the 0 at the end. Yeah. And then this was a negative immediate, so you did need to do the flip the bits and add 1 to get to the negative value here. All right, any questions? Yeah. Yeah, so when you see 10 to 1, that means it's bit 10, then bit 9, then bit 8, then 7, 6, 5, 4, 3, 2, 1 in that order. Yeah. Yeah. Otherwise it would be 1 to 10 or something. Yeah. Keep in mind that because we're reading from left to right is bit 31 down to bit 0, that's kind of why we're reading in that order. Yeah. Any other questions? Okay. So it's a nice toy to play around with this. I almost find it kind of like meditative to do this over and over. Right? Like once you get the hang of it, it becomes kind of calming. But yeah, definitely practice with this. I unfortunately cannot give you this code because it is going to trivialize some of the homework questions. But if you're interested, you can definitely write this code yourself. This is just a Python script. I do set the immediate so that they're within like a small enough range, so they're relatively easy to compute. You don't need to do complicated math for this. But yeah, the biggest part is just this giant table of all the instructions with their opcodes and func3s and func7s. All right. So if we have a bit more time towards the end of this class, we might come back to this, but otherwise, that's the last practice we'll have on that. Yeah. So just some concluding notes on the instruction formats. Let's take a look quickly at how we can handle immediates that are larger than the store value that we're dealing with. So first off, each instruction format has a different number of immediates, or has different immediate formats. For R-type instructions, how do you handle immediate larger than the size of the immediates that's allowed for an R-type instruction?
Wait. R-type has an immediate?
Trick question. R-type doesn't have an immediate. So we don't need to worry about that. For U-type instructions, the largest immediate is also the same as the largest possible numeric value there. So you don't really need to worry about that for U-types either. How about for I-types and S-types? I-types and S-types, they do have an immediate of maximum length 11 bits or 12 bits. So that's plus or minus 2 to the 11. What happens if you need an I-type instruction that's larger than that? Does anyone have a strategy or solution that they might use? Yeah? Multiple lines of code? Yeah? How would you do that? Okay, so if you have a larger number, you just add repeatedly until you get to the amount. That does work. It does take a lot of lines, potentially. Is there a way to do this in 2 lines guaranteed? Well, I guess 3 lines. Yeah, use a U-type instruction. If you want a U-type instruction, you do need to load that variable into somewhere. But that's effectively what you do. You take a temporary register, you store the immediate in it with an li, which might split into 2 instructions, and then you just apply that. S-type instructions, similar. So here's kind of an example of how you might do this with XOR I. For loads and stores, what you can generally do is you can add the offset first using an li and then an add operation, and then do a 0 offset load. So this is kind of what we see in a lot of store and load instructions. When you want a variable offset, like when you're iterating over an array, what you sometimes do is you just you increment the value of the pointer itself, and then do the do an offset of 0. How about for B and J types? Branch instructions, they're only going to be within 1,000 instructions, which is a lot. Most of your code is not going to have 1,000 instructions in a single while loop, but it still is possible to exceed. J-type instructions are a bit harder to exceed because you get up to, what, 2 to the 18 instructions? That's 250,000 instructions. So as long as you don't have a megabyte size executable, you should be fine. Although keep in mind that the Linux source code is 20 megabytes in size. So you are going to end up dealing with this sometimes. How do you handle jumps that are longer than this?
One defect jump and multiple J-type jump. Oh, one G.
So you do a large J jump and then you do a B jump.
I do a B jump first and do a large G jump. A B jump to the G jump.
Yeah. So for B-type instructions, that is a good solution. If a branch is within 1,000 instructions, you just branch normally. If it's more than 1,000 instructions, then what you can do is you can invert the condition to skip a jump or an unconditional jump, and then jump to the label, kind of like this. This works the exact same way as BEQ T0 T1 label. The only difference is we're using a J-type instruction jump instead of a B-type instruction, so we get a larger distance. This still doesn't solve the problem if we have a distance larger than 2 to the 18. How do you think we can handle that? Jump twice? Well, if you jump twice, you're only a maximum of 2 to the 19 instructions. If you want to go, for example, 2 to the 24 instructions, that's what, 64 jumps you need to do? I don't want to do 64 jumps for this. I want to do this in 2 instructions. Any other solutions? This one's actually a bit tricky. What you can do is actually this. So if jumps within 2 to the 18 instructions, you just do it normally. But if it's more than 2 to the 18 instructions, you can load the instruction with AUIPC. And then you use JAL-R to jump the rest of the distance. So this is why AUIPC exists, because you need to potentially jump larger than 2 to 18 instructions. This is also why JAL-R has that offset there, because using that offset, you're able to do this with only 2 instructions instead of adding AUIPC, then an ADI, and then a JAL-R. Yeah. Any questions here? All right. So all this information is available on the reference card. You can take a look through that later. We will be providing this on any exams, so you don't need to do any memorization of this. So here's the quick links. You go to the reference card, and it has everything you need to know. All the R-type instructions, the I-types, the I-star types, loads, stores, branches, the 2 jump formats, AUIPC, LUI, eBreak, and eCall, and the one extension operation that we will be using, which is multiply. But we'll never ask you to translate this, so we've omitted the opcode for this class. Here you have a list of all the registers. Here's all the instruction formats. Here's all of the pseudo instructions that we will teach you in this class. So as well as their translations. There are a few other pseudo instructions, including one that'll show up in today's lecture, but we're going to specifically not teach you this because it is bad practice to use them, at least for your level. Other than that, we also have the ASCII table, floating point precision, a nice diagram on how floating point works, SI prefixes, C formats. Boolean algebra is something that we'll be covering next week. And then the rest of this is stuff for later in the class. So it's a good resource. You'll be able to use this for any exam that we cover. All right, that concludes the instruction formats. Let's move on to today's main topic. So we've basically covered all of RISC-V and how we translate that even further down to raw binary. Let's kind of do a brief overview of this entire class so far. We started at C. We moved all the way down to binary. And let's just walk through that entire process. So when we say we compile code, when we're talking about it colloquially, just informally, we generally say that the compilation process starts at a C file and it converts it into an output executable. So that's what we'd say, like, if we're just speaking informally. In effect, we run gcc foo.c. It produces a.out through some unknown process. In reality, it's consisted of 3 steps. The compiler step, which converts it into an assembly file. The assembler step, which converts it into an object file. And then the linker step, which converts it into an executable as a whole. There is one last step that we call the loader, which is kind of the process of just running the code itself. So the compiler, what it does is it takes your high-level codes, for example, your C file, and it just translates it into an assembly file. So, for example, foo.c turns into foo.esc for a RISC-V format. Now, this can include pseudo instructions. It can include labels, all the things you can do with regular RISC-V. It isn't fully done yet. It is just conversion into assembly at this point. The assembler, it'll take that code and it'll translate that into binary. So it'll take the assembly, turn it into binary. So foo.s turns into what we call an object file called foo.o. This isn't just the binary of the instructions. It's also a few pieces that you need in order to compile it or to break it down further into an executable. As an example here, certain headers, any libraries that you're adding, we don't actually add these into the file yet. We'll wait until the linker step to combine multiple executable files together. So the linker is where we take a bunch of these object files, one corresponding to the code you wrote, maybe one corresponding to some library you used, and we combine them into a single output executable. So this kind of lets you compile things separately. If you have, for example, standard IO, that's a huge file. We don't want to recompile it every single time. So we just leave it in an object file format, and that way we can quickly combine these two together on the fly. This is especially true for standard IO because you never actually modify it. If you are modifying standard IO, then I believe something has probably gotten wrong. The most common reason why standard IO changes is because you accidentally installed a virus and the virus decided to add code to standard IO. So do not change standard IO. The last step is the loader. And what it does is it takes your executable, your a.out, and you just run the program. So it kind of converts from the executable code to whatever program behavior you were looking for. So in effect, what it does is it just loads it into memory and starts running it. Any questions about the general structure of this? All right. Oh, yes. Is there ever a reason for you to interact with the compile to assembly code? Yeah, so these files are accessible. You can use certain compiler flags to open up each one individually. While you're still learning, it's a good idea to just open it up and see what's happening under the hood. It's just nice to peel back the layers and see what's going on. In practice, one thing you can do is if you're running into this really weird bug that you just can't solve, there is a non-zero but very low chance that it's the compiler's fault. So you might actually just open the assembly file to see what's going on. There are actually ways that you can write assembly code in your C and have it compiled directly. It's called ASM, but those tend to be a bit harder to work with, a bit more unstable. So it is useful in that case to just look at the .s file to see what's going on. The object files, those are mostly not human readable, but you can get a sense of what's going on in practice. You can actually just open an executable in a normal text editor, and you can see a lot of things. For example, remember how I said all static strings are stored in memory? Well, it's actually stored in part of the executable. And if you open a file in a text file, then you'll see a lot of those static strings just lying around in plain text somewhere within the file. So you can kind of see some of these things if you want. Other than that, there's not really too much practical purpose. If you're just writing at a high-level language, you don't need to ever go through this process and look through this. In practical industrial settings, you're probably never going to be doing this most of the time. But it's useful that you have that option, just in case. Yeah. Any other questions? I'm assuming that's not a hand. You're just putting your head in your, yeah. All right. So let's go through each of these steps in more detail. So here's what the compiler is. As a reminder, what it does is it just translate our code from C to an assembly language. So this is actually one of the trickiest parts of the steps. Human language is just very fluid and flexible, right? There's a lot of different ways that you can say the exact same thing. And humans are used to that. This is how we try to communicate. We like different ways to communicate the same thing because it enables us to write some nuance into something. High-level languages, they tend to have that flexibility as well, right? C programs, right? You can write a single line of code that does 5 different addition operations or 10 subtractions followed by a left shift. There's so many different ways you can write a single line of code in C. And you have to figure out a way to translate that into a simpler language like RISC-V. In order to do that, you need a program that can understand that flexibility, and that's very difficult. The reason why humans have it so easy is because we actually have a brain structure called the Broca's region, which is dedicated specifically to language acquisition and language recognition. Computers don't have a Broca's region. And because we have a Broca's region, we don't know how to consciously translate stuff that easily. It's just done automatically for us, and we don't really know how to do it consciously. So it's actually very difficult to write a compiler. We're not going to go into too much detail today. A lot of the information within this next session is actually considered a bit out of scope. You don't need to really know about this. But if you want more info, CS164 is an entire class on how to write a compiler. In fact, it is a sequence of 4 projects which end up writing a compiler over the entire semester. It takes that long to write a full compiler. And if you want, you can take some linguistics classes. One of our head TAs, Andrew, who was running lectures last week, I believe they're also a linguistics major, so they might have some good advice on that. Ask on Ed. All right. So the general steps for compilation are as follows. So we start off with just pre-processing. This kind of just handles all the preprocessor commands, any macros, effectively anything in a C program with the hashtag at the start. So this technically happens before compiling starts because after you pre-processing, you're still left with valid C code. I call it part of the C compiler, but it's really part of the pre-compile step. It doesn't even count as compilation yet. After we do all this pre-processing, we now have a pure C file with no macros. What we'll do is we'll split it up into tokens. So this is called the lexer. And what it does is it just reads through the file and splits up the words within the file into individual meaningful components. So for example, if I had the line int main open parentheses, close parentheses, there's 4 main tokens here. We have the int token, the main token, open parentheses token, and close parentheses token. Each one within our language has a specific meaning, and it has a well-defined separate meaning. This is unlike, for example, if I did in versus mat, and in open parentheses and close parentheses. Those aren't tokens with meaning in and of themselves. So the lexer is tasked with figuring out how to split things up. How many people took 61A here? Did you do project 4? There was a scheme interpreter. If I remember correctly, the first step involved splitting things into tokens, right? So you've done something similar there. Yeah. The next step is semantic analysis, which is called the parser. And what this does is it kind of reads the sentence structure, the sequence of tokens, to determine how the sentence is structured, what its meaning is. When you did the scheme interpreter, scheme itself is just a very simple language. It has a very simple structure because everything is parentheticals and everything. So you didn't need to do as much complicated things for parsing. For a language like C, where you can write down arbitrarily many operations within a same line of code, it's much more complicated to figure out what the actual structure is. You have a lot of theory behind it and figuring out how it works. So this is where the majority of the linguistic analysis comes into play. Because you can use the same analysis patterns for analyzing C code and apply it to, like, for example, English, and get a pretty good sense of how the language works. So a common example is the star token. If I just tell you to do something with a star token and I didn't tell you the context, you wouldn't know whether I mean star as multiply or star as in dereference. There's all sorts of these quirky syntactic structures within C. So this is really a difficult process. It often uses a syntax tree, which is just a way to show how the structure of a sentence works. If you ever used like sentence structure trees in an English class, I think I was taught that back in like one of my high school years, but I don't remember it fully. It's kind of like that. Now, after we've parsed the sentence structure, this is a good point to start doing optimizations. Now, it used to be that compilers were very simple. They didn't really have much processing power. It wasn't really easy to do optimizations. The idea was the compiler was designed by one person, right, or someone. And at that point, a compiler that was designed for every other program in existence, it probably isn't going to do as well a job as the programmer who knows specifically what you're dealing with. Nowadays, we've written compilers for the past 50 years, and it's kind of different. Who do you trust more to like optimize your code? You who knows actually what the code is, or someone who doesn't know what code you're working with, but who's had 50 years of experience to iterate over and develop ways to optimize stuff? It starts to get a bit trickier at that point. Nowadays, most of the time, optimizations are actually better than how humans can do things, because you're relying on 50 years of better programmers to compile things. Now, you can adjust the level with compiler flags. Generally speaking, higher level compiler flags take longer to run because it takes a longer time to find these optimizations. Overall, if you get good enough at programming, I believe you can still beat the optimizer, but it is tricky as you go. So finally, after you finish optimizing, you start encoding it into a new language. You effectively generate the code. You output it as, for example, a RISC-V file. So this is all kind of arbitrary and conceptual. Let's take a look at an example. So we're going to compile this code from C to RISC-V, and we'll just be coming back to this file every single time we, or every single step of call. So here's our file. What does this code do? Anyone? Yeah. Yeah, print hello world 10 times. All right. We are going to be looking for eventually a compiled file that prints out hello world 10 times. So let's go through these steps. Our first step is the preprocessor. So we take this file. Here is the only preprocessor command that we'll be looking at for now. The include statement is a preprocessor command, but it kind of just notes that we have this library that we need to connect to later. So we won't talk about how that actually translates in C compilation. But in any case, what do you do here? Well, a macro, all it does is it replaces the line iters with the next thing. So we convert this into this. So we take iters and replace it with the number 10. This is our pure C file. This is after the preprocessor is done. Now, the next few steps, I'm going to just skim through these because you don't really need to know too much about them. So we start off with the lexer, which kind of just splits things up into the individual tokens, gets rid of all the information. Here, I've split it up into these tokens with spaces. So every time there's a space, it's going to be a new token. Then you take the parser. Now, I didn't run this through an actual parser. I tried to do this manually. And I wrote the abstract syntax tree in kind of a format that was easy to write, not necessarily the way that you'll see it in practice. But here is the structure. It is a lot more information. But you kind of see the goal, right? You're defining a function which has type int as an output, no parameters. It starts off by writing these variables as local variables. Here's the body of the code, which is composed of a for loop, which is initialized with an assign statement with the variable I set to 0 and a condition, which is a less than condition, with the left side being the variable I, the right side being the constant 10. It's all the data that you need to figure out what it means. Converting to this format is very difficult for a computer, but it is possible. After this, the optimizer might run, but I don't think there's any real ways to optimize this. And then we'll just encode this into this. And this is going to be kind of our RISC-V file, the file at the end of this process. Any questions up to here? All right. What is the program language of a compiler? Good question. It's up to whoever decided to write compiler. The compiler needs to be run on your code, so it does need to be an executable. But the common approach nowadays is to write your compiler in a programming language like C. So this is called bootstrapping, where you start off with a weak compiler that doesn't compile very efficiently. You need to get it from somewhere, but you start off with that, but then you use that to compile a more complicated and faster compiler. And then you use that compiler to compile an even faster compiler. And you keep doing that a few times until you get the target compiler that you want to. This does mean that in order to get a C compiler on your computer, you first need to have a compiler for C to compile the C compiler, which is a bit of a catch-22. It's called bootstrapping specifically because it's referencing to the statement where you're pulling yourself up by your own bootstraps. It is possible. Kind of the way you do that is you just find an executable for a weak compiler that's available online. It's not going to be specifically optimized to your system, but the C compiler, the compiler written in C is going to have ways to optimize according to your system and make a better compiler as a result. Yeah. Any other questions? If not, let's take a few minutes break. Let's come back at 2:56 according to that. All right. It is 2:56. Let's bring everyone back. All right, mic on. All right. Let's keep going. So now that we finished compiling, let's take a look at the assembler. Now, because we're not talking too much about the compiler, the assembler is going to be the part where we look at in more detail, or in the most detail. So in effect, what we need to do, the main steps that we need to do is we need to take all the pseudo instructions and replace them with true assembly instructions. We also need to kind of resolve as many of these labels as we can. Our goal is to produce an object file that contains both all of the code, the text, and the data that the assembler needed, plus any information that later files need. For example, linking, and another example, debugging. Now, how can we do this? Well, a lot of instructions just already have all the information you need within the instruction itself. Like add instruction, you can just translate that into binary directly. Add-I, you can translate it into binary directly. Pseudo instructions, they also have well-defined conversions to regular instructions. You just use the lookup table to figure out what you need. It's a very nice one-to-one relationship you can do here. In effect, anything that's position independent can be computed. The things that you need to worry about are things with labels. Now, for some things like branch instructions, labels should be close enough that you can get access to them. Most JALs will also be PC relative because you're jumping to within your own file. But if you're relying on some file that's external, you might not be able to do this. In effect, once we convert every pseudo instruction to real instructions, we should be able to handle all the things that jump within our current file, but we can't handle anything that jumps outside the file to something else. So we just need to determine the offset to encode that, and we'll just write out those numbers everywhere. So in order to do this, the assembler is going to do 2 passes over the program. Kind of the reason why we need to do that is because sometimes we might have these forward references. For example, this BEQ, if we're just reading through this file in order, we see the loop line here. We see this BEQ is asking to go to exit, but I haven't seen an exit label yet, so I can't jump there until later. After I keep going here, I see J loop. Oh, I've seen loop earlier, so I might be able to connect this. But I don't see exit until here, which means I need to run through this a second time to get back to exit. So in order to resolve this, we just go through this 2 times. The first pass, we just remember the positions of all the labels and resolve any pseudo instructions. In the second pass, we just go back over every single time a label was used to generate the machine code associated with that. Now, if you have a reference to another file, like calling a strlen comes from the C string library, or any references to static data, like a load address to a data segment, you can't do this yet. Because of that, because you need these absolute addresses, you'll just leave those unresolved in 2 tables. The 2 tables that we use are the symbol table and the relocation table. We'll go over exactly what these are in a bit. For now, let's come back to our C file, or our print hello world program. There's a bunch of things that I didn't cover here. These are called directives. They're kind of like C preprocessor commands in a sense that they're directions to the assembler, not code in and of themselves. They're often generated by the compiler in the previous stage because they're useful to tell the assembler what to do next. Again, they don't provide machine instructions, they just provide information on how to build the parts of the object file. Here are common examples of these directives. For example, .text, it's saying that the next bit of thing that I'm writing should be a text file in the sense that it's the machine code. Here we use text interchangeably with code because that's just how RISC-V decided to define what the code segment is. .data similarly puts things in the data segment, which is the same as the static segment from C. .global, it lets you define a label as a global label, which means that other files should be able to access this. This means that, for example, the main label here, that should be accessible to other files. They should be able to call the main function. Whereas, for example, this loop, which isn't intended to be an actual function call, that should not be accessible to outside files. .string stores a string. .word stores 32-bit integers. There's other ones here. For example, .align lets you align to a certain number of bytes. .row data is basically .data, but RO, meaning read-only. .section is just another section. Yeah, there's a bunch of these. You can look them up in your own time. It's cool to look to see what you can do with these. Any questions here? Okay. So let's run through the assembler. I'm going to go through two passes. The first pass, we just need to look through everything. I'm going to copy over the text or the raw instructions on the side, and anything that gets stored in the symbol and relocation table over here. So first thing that the assembler does is it looks at this line. Well, .text, then .line 2. What does this do? Well, it aligns the text to be a multiple of 4 position. So now the text is going to start on a multiple of 4. Here I see .global main. So I'm going to mark in the symbol table that I need a global variable main that will exist at some point. Okay. What do I do next? Well, I take the main, the first line, which is addy SP -4. I'm going to mark this in the text here as line 0. Now, in practice, it's going to be the binary of this instruction. But I didn't write out the binary because it's hard to translate back and forth immediately. When you see instructions in the text, pretend they're the corresponding binary associated with them. Now, we also note that we found the main label. We saw that it was a global main label. So I'm going to mark down that this is located at location 0 relative to the text. Next, we do store word RA0SP. That's just a pure instruction. We can just store that on line 4. What do you do on the next line? What are we going to store? What happens when we evaluate the next line, LIT010? Yep. The LI can translate into an ADDI T0x010, so we're going to do that. What about the next line? Well, we're going to see a BEQ. We don't necessarily know where the end label is. So I'm just going to mark that down in the relocation table, saying, hey, at line 0C, there is a label called end, which I need to resolve at some point. And at the same time, I found the label loop, which is a local label. I haven't seen it in the global set. So I'm going to mark this as 0C, located in text. Okay. What about for LA? What does LA translate into? Load address. But that's a pseudo instruction, so I can't use LA in the text file. What do I translate this into? Well, we don't know actually where the string is going to be. So I'm going to want to put in an absolute address here. What I'm going to do is I'm going to translate this into an LUI and an add-I instruction. We don't really know where it's going to be. So I'm just going to leave it as question marks for now because we don't know what stir1 is. We do the same thing for LA at A1, stir2. 1.8 plus 1C, those two lines have the stir2 label. We don't know what to do with that. Yeah. The next line is call printf. We didn't discuss what call is, but call is effectively the larger distance jump pseudo instruction for JAL. So JAL, you only have 2 to the 18 instructions to jump to. Call, you have an arbitrary number of instructions, but it is a pseudo instruction that translates into a smaller instructions. Anyone remember what those two instructions were? AUIPC, and then JAL-R, yes. So this line is going to turn into an AUIPC plus a JAL-R. We again don't know where printf is, so we'll just leave this as that. Next line, is there anything special going on? No. It's just an add-I instruction. We can just put it in immediately. JLoop, anything special going on? We do have a loop label. Now, depending on how you're doing this, you might resolve this now. I'm just going to choose not to resolve this at this point and come back to it later. Again, depending on the exact compiler you're working with, you might decide to resolve this now because you already know where loop is. The next line, we do find the end label, which is located at location 30. And we take the load word RA0SP. Line 3, 4, add ISP 4. That's just a regular instruction. LI, we translate that pseudo instruction. RET is also a pseudo instruction. Anyone know what that stands for? It stands for return. What does it turn into? What real instruction does it turn into? Anyone? Well, what do we want to do when we call ret?
Fit the current function to the previous space.
Yep, which is where? Yeah, it's a location that's stored in RA. So what do we want to do?
We make the state of RA.
Is there an instruction that lets us do this? JR? Yep, we can do JRRA. The only thing is JR is also pseudo instruction. In fact, JR is a pseudo instruction for what? Yeah, JR is a pseudo instruction for JAL-R because every JR can be done with JAL-R. And in fact, what we do is we do a JAL-R. What's our destination register? What do we set our, which variable do we set to PC plus 4? Well, that's for a jump to a function call. But when we're JRing, we don't actually want to come back ever. Yeah, we don't actually have a return address location we need. So we just try to set it to x0. So we kind of ignore that part. And lastly, JAL-R takes in as input an immediate. What immediate do you think we want to use? 0. Yeah, because we're not jumping any distance from the RA. So this turns into JAL-R x0 RA0. At this point, we see section dot read only data be a line. That means that we're no longer writing in the text section, we're writing in the data section. And we're going to byte a line to a 4-byte location. So stir1, we find here, it's a string, hello, comma, %s, exclamation point, \n. And we're going to store that in our symbol table, location 0 data. How many bytes does that string hold? 11.
Oh, wait.
13.
No.
12.
Backslash many. What? So, and
10.
one.
1. All right. You had HELLO, comma, space, %S, exclamation point. You are correct. That is actually a single character in new line. Null terminator.
Wait.
Yeah, you have that null terminator. I actually miscounted this when I did this early in the morning, so I actually thought this was 13 characters, but you are right, it is 12 characters here. Yeah. So after that, you just put world. I accidentally added an extra byte of space. Sorry about that. But yeah, this one is going to be 6 characters long, or 6 bytes long as a string because the null terminator counts as an extra byte. If you're saying the number of characters long, then you might call it 11 characters long because that's its string length. But it still does have that null terminator at the end. All right. Now that we finished our first pass, we'll go over our relocation table to find any labels that we can manage. First off, we'll look at end. Have we seen a symbol end yet? Yeah, we've seen it here. So end, the variable is located at 0C. The end label was located at 30. How far do we need to jump to go from end to, or from 0C to 30? And all of this is in hex, by the way. I've been ignoring all the 0x's because I don't want to write a bunch of 0x's.
4 in hex.
Yeah, 0C plus what equals 30? That's the same as 30 minus 0C, which if you do the hex math becomes 0x24. So we'll replace this with the number 0x24. Now here I'm writing 3 hex digits, mostly to showcase that this is a 12-bit, 13-bit number. Next, stir1. Have we seen a stir1 label yet?
Yeah.
It's located in the static section. Do we know how much to jump from text location 10 to data location 0? No, we don't know this yet because the text in the data section might be moved a different amount of space later. So we're just going to leave this unknown for now. Stir2, anything we can do with that? Nope. We can't do anything yet here because we don't know how far we need to jump for this because, again, the data section and the text section, they might move to different distances from each other. Printf, have we seen printf before? Nope. We don't know what printf is at this point. Hopefully the linker is going to tell us what it is. So we'll just leave it alone for now. Finally, what about loop?
Yeah.
Yes. All right. So where's the location of loop?
Minus 0.
Yeah. The location of loop is here. We need to go minus 20 in distance. Which corresponds to the hex number 0xFFFE0. Now at this point, we can kind of clean up our relocation table and symbol table of things that we don't need. Any local labels, they shouldn't be necessary from now on because we finished assembling this file. So we can delete those lines. At the same time, any relocations that we've already managed to handle, we should be able to delete as well because we've already handled those. So in the end, we are left after the assembler with this code. A text file consisting of mostly compiled assembly code, or mostly assembled code. A data segment consisting of all the strings. A symbol table consisting of all the labels that we don't, or that we might need in the future, and a relocation table consisting of all the labels that we need to fix. Now, in practice, you can't just add a question mark to a location. all these question marks are going to be zeros for now when we send this to the linker. But I'm leaving these as question marks just to showcase that we don't necessarily need to know what they are. They're going to need to be replaced in the next step. Any questions here? All right. So once we have this, the object file is fully constructed. And the way that works is that we start off with an object file header that just shows the size and positions of all the other pieces. It's kind of like a table of contents for the rest of the file. We then have the text segment that has all the machine code, the data segment, which has all the static data, the symbol table, which we saw, the relocation table, which we saw, and then maybe some debugging information at the end if you use certain flags. A common standard format is the ELF format. It's well known for starting off with the letters ELF. Everything except for Microsoft uses it, basically. Microsoft decides to go fancy and do something else. So the symbol table, it lists all the items in the object file. It's used by GDB to kind of see what those labels are. So these are these instruction labels. Any global directive tells you that a label can be used by an external file. Anything in the data segment marked with data directive, those are also global variables that may be used by other files or used by the current file, but you need to know how far this data segment is from the text segment. The relocation table is just a list of all the things we need to do next when we go through the linker. Anything we still need to do, so like any external labels, jumping to, for example, libraries. Also, any data stored in the data segment, for example, static variables. Any questions on the assembler? Okay. Let's move on to the linker. We've already gotten our object files. We have our symbol table and our relocation table. We have the text mostly converted into executable format. We just need to fix all of those remaining labels, and we need to combine them with other libraries. So this is where we start combining multiple files. We don't need to compile libraries separately each time. We just need to link them together. Here's kind of how it looks. We will start off by putting together the text segments from each file. Then we put together the data segments. Then maybe any of the separate metadata, all the information. After that, we'll resolve all the references. So we'll go through the relocation table, handle each entry, and then we'll be done. We'll have a fully compiled file. So for RB32, the linker kind of assumes that the first text segment starts at address 0x10000. Anything below that is kind of treated as a barren no man's land. You're not allowed to put anything there. In practice, the computer might decide to put it at a different location in its physical memory, but we'll talk about that later once we talk about virtual memory. The linker knows the length of each text and data segment. It knows the ordering of the text and data segments that it needs, and it calculates an absolute address for each label. It also resolves any references. So it'll search for any references in the user tables. If it doesn't find it, it'll search in the library files. And once the absolute address is determined, then it will fill in the machine code fully. At the end, the linker should contain an executable with the text and data segments, along with any headering and debugging info. So let's come back here. The left side is the Hello World program that we had running. Our goal at the end of this is to fill out the rest of the relocation table. The symbol table on the right is for stdio, that library. I've kind of omitted a lot of this stuff. I'm going to imagine that it takes over 0x1000 bytes, which is actually much smaller than it should be. But it's a massive number compared to the 0x40 byte size of the text on the left side. And let's say that printf is located at 0x800. So our first step is we're going to need to let the linker do its thing and figure out where it wants to put stuff. We're not going to go into detail about how it decides this. We'll just say that, for example, it decided hello world goes at 0x10000. This stdio text starts at 10100. And the hello world data starts at 10008000. I just picked these numbers semi-randomly. So what do you do first? We should look at stir1. Where is stir1 located? It's located at location 0 relative to data. Where is data located? 0x10008000. So what is the absolute address we should be setting stir1 to be? Yep, this address. We need to split this into an LUI and an ADDI. So what's the LUI going to be? Yeah, 10008. What's our ADDI going to be? 0. ADDI A0A00 does nothing. Can we just delete that line? Someone said sure. Someone said no. Why no? Yes. It might mess up other jumps. Yeah. Right now, we've set it up already so that all the jump labels have already been addressed, which means that if you're jumping across this, then you need a specific number of instructions between there. Because of that, we can't necessarily get rid of this. Maybe if we decided to go through another pass and fix all the jumps later, but that is going to require a lot more complexity in the linker and the assembler. So we're not going to replace this line and get rid of it. All right, next line. Stir2. Where is that located in memory? Stir2 is located D offset from data, which is what address?
1080D.
Yeah, 100080D. So we need to set that. What do we put in for the immediate line 18 or 18? 10008. What about for line 1C?
0xD.
0xD. Yep. And then lastly, we have printf. Where is printf located? Printf is located 800 relative to the, sorry, that should be text there. I'll fix that later. It's 800 relative to the standard IO text, which is located where? 10100. What's 10100 plus 800? Yeah, 10900. Yeah. Now, one thing here is that this is not a absolute jump. This is a relative jump because we're using AUIPC and JAL-R here. So we need to count how many lines or how much memory or offset this location, 10900, is away from the start AUIPC, the line 20. Keep in mind that because the PC is computed at the AUIPC line, we're jumping relative to line 20. So where is line 20? Where is this AUIPC located? It's 20 offset from 10000. So where is it? Yeah, 10020. So hello, or the printf is located at 10900. This line is located at 10020. How much is the offset? How much jump do we need?
-80.
Huh? Sorry, do you? Sorry, this should be a text. I wrote this wrong. So the text is located at 10900. The hello world is located at or the AUIPC is located at 10020. The difference here is
80.
yeah. I did the math entirely wrong. All right. Pretend that 2 is an E. Whoops. That is an E. All right. So if we want to convert this to an 8E0, what do I set to be our immediate up here? What is our AUIPC offset? It's the first 20 bits of this immediate, which is what? And you wanna what's the top 20 bits of this? All zeros. Do we set the AIPC to 0? What's our what would this next line be? Yeah.
Oh, yeah. It's 110, so it's 1, and then next time that is the 1.
Yeah. You set it to 1 because here we run into that same bug from earlier where if you set it to 0 and then do an 820, the 820 is treated as negative number instead of a positive offset. Yeah. So because of that, we set it to AUIPC RA1, and then we JAL R8 to E0. At the end of this, we have a fully written executable. All of our offsets are defined. You should be able to just run this directly. And in effect, we're done. We have managed to convert our C file into an executable that we can just run on our computer directly. Now, as an aside, so far we've been describing the kind of the traditional way of doing things with statically linked libraries. The library is kind of part of the executable. The library updates, you don't get a fix because the library is part of the file itself. A good thing is that the executable is self-contained. But even if not all of it's used by the user program, the executable ends up including the entire library. That's kind of inefficient, especially when standard IO is really big. So an alternative is to use a dynamically linked library, which is common on Windows and Unix platforms. This library is run as a separate executable when you load. And when a call is made to the library, we just kind of ask the library to run it for us. The idea here is we never actually fully link this into the code itself. We just handle it on the fly as we're running this. Here's kind of the advantages and disadvantages. Oh no, my computer's running low on battery. So one of the big advantages for a dynamically linked library is that you don't require as much data or as much memory space to store a program. If you're not including a million byte libraries, then you don't really need to store as much data. Also, if two programs use the same library, you don't need to have two copies of that located in memory. You can just use the exact same copy of the library that's been dynamically linked. The one cost here is that you do add extra overtime to the linking process because you need to figure out where it is. You can't just jump. It's also easier to upgrade libraries. So if you upgrade a library, it updates every single program that uses that library. This does cause potential compatibility issues, and it does mean that having the program executable isn't enough. Now, overall, that does add a lot of complexity to this, but generally speaking, it is considered a worthy trade-off. That's why a lot of systems like Windows systems use dynamically linked libraries internally. If you're having a statically compiled code, back when computers were slow, it used to take hours to compile code. So this led to this XKCD comic about how the #1 programming excuse for slacking off is that the code's compiling. The alt text describes how you can even like steal like office supplies because your code's compiling. Yeah, so you can't say this anymore, unfortunately, but you can still say something like your Git repos rebasing or something. All right, one last part for today. The loader is effectively just the part where you just run the code. It's actually part of the operating system, which we're not covering too much in this class. Take CS162 if you want to learn more about that. In effect, what it does is it loads the program into the newly created address space. It reads a.out for the text and data segments, creates new segments large enough for this, plus the stack segment. It'll copy over those instructions and the data. It'll copy the arguments, pass it onto the stack. It'll initialize all the machine registers. In RISC-V, everything is set to 0, except for the stack pointer, which is assigned to the first free stack location, and the GP and TP, which we are not talking about. It'll jump to the start of the main routine. And then if the main routine returns, then it'll terminate with an exit system call. All this is handled by the loader, which is part of the operating system. All right, this last part is an optional section. Due to time, I'm not going to cover it. Feel free to look through this if you want. It is not going to be considered within scope of the class. It's kind of discussing the difference between Python and C. All right, that's it for today. See you tomorrow.